In this fifth module of Chapter 9, Module 9.5, I will cover the estimation of population growth rates based on either the change in number of individuals in a population over a specified time period or through population age structure. Both concepts are simple and straightforward. Growth rate from population number. The two models shown here are for the computation of growth rate and for population projection. The first is discrete time. We have lambda, the finite rate of increase, equal to the ratio of the number at time t plus 1 relative to the number at time t. The projection model is the number of individuals at time t equal to the product of the initial number in the population and lambda raised to the tth power. The continuous time version of these models is little r, denoting the intrinsic rate of increase, equal to the natural log of lambda. The continuous time projection model is the number at time t equals the product of the initial number and e raised to the product of little r in time t. A simple example is shown in the table for computation of the growth rates and projection of the population models. We have in the first and second row of this table time and number at time t. At time t equals 0, there are 100 individuals in the population. At t equal 1, there are 121, then 137, then 159, and finally 183. Thus, lambda equals 1.21, which is computed as the ratio of the numbers at time equal 1 and time equals 0, and little r equals the natural log of this lambda value, or 0.191. And the remaining rates are computed similarly. The geometric mean of these for lambda values equal 1.162, and the arithmetic mean for the little r values is 0.151. Using time t equal to 10 and the initial number equal to 5 individuals, the discrete model yields the product of the initial number 5 and 1.162 raised to the 10th power, the value of which equals 44.8. Computations in the continuous model using little r equals 0.151 yields the same result. Growth rate from age or stage structure. Estimating growth rate using age structure is shown next. Consider this table with time across the top row and number in the 3 age classes in the first column. We have the numbers at each time in each age class that are doubling every time step with respect to both age and therefore also with respect to time. Note that horizontally the numbers increase by twofold within each age class as well as by every time step. And vertically downward the numbers decrease by 1/2. It follows that we can infer that population growth rate is doubling every time step if we assume no mortality. More formally, this relationship can be denoted by letting nx and ny equal the numbers in the age classes x and y respectively. N equals total number, and cx and cy denote the fractions in the population ages x and y respectively, and b equals birth rate. Therefore, the fraction age x, denoted cx, equals the number at age x divided by the total number denoted n. And the same relationship holds for the fractions at age y, denoted cy. Equating these two yields this ratio equivalency. Now let cx equal the birth rate times e raised to the product of minus r and lx. And let cy equal the birth rate times e raised to the product of minus r and ly. Based on the previous relationship, we can express the ratio of the fraction at age x to the fraction of in the population at age y equal to the right-hand expression. With birth rate b canceling out in both the denominator and numerator, we have the ratio of the two exponential terms to the right, which equals the ratio of the fraction in each age class. Solving for r in this expression yields this formula where t1 and t2 equal the ages x and y respectively. An example computation based on the ratio of two stages in a population is shown here. With sample in the top row, number in the egg stage and immature stage in the next two rows, an estimated value of r is given here. The mean difference in ages of these two stages is 5 days. The natural log of the ratio of the number in the egg stage and the number in the immature stage yields a value of 0.206 for the estimated population growth rate for the first sample. Growth rates in subsequent samples are computed with the same formula. As I noted at the start of this module, these computations for estimating growth rates based on differences in numbers at 2 times or on the relationship of age or stage class in a single sample are simple and straightforward. This ends Module 9.5 of this 9th chapter.